Now we will find about the electric potential at any general point due to an electric dipole. So for that we look we look in this figure. This is an electric dipole which consists of a charge minus q and plus q placed at A and B, and they are separated by a distance to A. Okay, right, let us consider any general point here. Let's say this is a point. When I say general point, mean it is a point which is neither lying on the axial nor on the equatorial line, but it is in between them. Let's say this point. Now if you join a line AP, OP, PP, then we can see the distance AP here, let's say it is R1, BP is R2, and OP is small r. Okay, also we will further imagine that this line to OP here, it makes an angle theta with the axial line. Okay, now if I extend this line in this direction till a point C, and from this point A I drop a perpendicular to the point C, then I get this triangle, and so this angle here again it should be theta, because right, it is a vertically opposite angles to this one. Okay, so now what is the electric potential at a point P? Right, just like before, the electric potential at a point P is usually equals to the algebraic sums of the potential at P due to minus Q and plus Q. So that means Vp is equals to Va plus Vb, Vp your Va is equals to, usually like this. What is the distance between this point and this point? It is R1. Similarly for here, it is R2. Okay, so now taking common small q, 4 pi epsilon naught. Then first I'll write this, and this minus I'll keep it like this. Next I simplify, I find out the LCM. Now for a short dipole, what will happen in this case? So for a short dipole, when I say short dipole, this length AP here, it is equivalent to AC. Okay, when the dipole is short, this point C will almost close to a point A. So if that is the case, then instead of AP I can say is equals to CP, but CP is equals to OC plus OP. See, I have written here, but OP is equals to R and OC is equals to A cos theta. Similarly for a short dipole, this small r2, it is nothing equivalent to only this distance dp, but dp is equals to OP minus OD. Your OP is small r and your OD is again A cos theta. So now substituting the value of R1 and R2 in this equation 1, you'll get like this. Next you simplify, you'll get this much. Okay, so for a short dipole, what happened in this case? For a short dipole, R square can be neglected compared to A square. A square can be neglected compared to R square. So if you neglect A square, then you'll get only this much. Or Vp is equals to P cos theta upon 1 by 4 pi epsilon naught P cos theta upon R square. And please remember, how do we get this P? Because it is an electric dipole moment, which is equals to 2AQ. So this is your equation 2. Now special cases. When the point P lies on the axial line, that means theta is 0 degree. So your V axial, that means the potential on the axial line will be 1 upon 4 pi epsilon naught P upon R square. Cos 0 is 1. So that's why we have only this. And when the point P lies on the equatorial line, so V equatorial is equals to 0 because cos 90 is 0. So again we get the same thing like we have derived separately before for the potential at an axial and the equatorial line, right? So same equations we are getting, or same results we are getting. So from the general point we can get back to the special case when the point is on the axial and at the equatorial. So please remember this topic carefully, because it may be asked again in exams, because I have seen this topic also is important. It is usually asked in exams also, so please take care for this.